Alright, hello, welcome. In this video I'm going to be working some related rate examples, and specifically I'm going to be working through BC Homework 4.3. But I'm not going to start with number 1, because if you are watching this along with me and you have not started them yet, I want you to focus most on the ones that are like towards the end that are what you would consider to be word problems. So I'm going to start with number 13. And then I'll do all of the problems on this set. I'm just going to start with number 13 so that anybody who's just tuning in and was going to do the homework alongside me, which I don't recommend. You know, if you were going to do that, I was just going to do these first because they're the most important. So the radius of a sphere is increasing at a rate of 2 inches per minute. I'll use some color this time. So radius increasing 2 per minute is giving me dr dt equals positive 2. Find the rate of change of the volume at r equals 6 inches. Okay. Note that the volume of a sphere is given by v equals 4/3 pi r to the third. All right. Like I told you, the formulas are generally given to you in line with the question. So what I'll do is I'll just start by, I guess, taking the derivative. I'll try a new pen today. Take the derivative of this thing, and I'm going to take the derivative of the 4 pi r squared dr dt. So dv dt is 4 times pi times r squared times dr dt. Okay. I've got r, that's 6. I've got dr dt, that's 2. So I should just be able to find the rate of change of volume by just plugging stuff in. So that's going to be 4 times pi times radius squared is going to be 36 times dr dt is 2, right? And then that's going to be a perfectly fine expression for the rate of change of volume. Okay. I would say that the rate of change of volume is going to be that number of cubic inches per minute, but for the most part, in general, they don't ask you for the units on these related rate questions, so you don't have to worry about it too much. All right. Spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant when the radius is 30 centimeters? This is going to be very similar to the last one, right? It's a sphere. I already gave you the formula up there, so I'm just going to copy it again. Okay, that's good. And, well, dv dt is, we just took this, is equal to 4 pi r squared dr dt. Okay. But the inflated at a rate means that the volume is getting bigger. And so I'm going to say that dv dt in this situation is positive 800. Okay. And so that's going to be 800 equaling 4 times pi times r squared is 30 squared is 900 dr dt. Okay. So if I needed to solve for dr dt, I'm just going to divide by all this stuff. So that's 800 divided by 4 pi and 900 on the denominator. Okay. Next one is a cube situation. And let's wait for a second. The edges of a cube are expanding at a rate of 3 centimeters per second. How fast is the volume changing when each edge is 10 centimeters? Okay, paper got all folded. All right, so the edges of a cube are expanding at a rate of 3 centimeters per second. In general, I just call the edge of the cube x. So dx dt is positive 3 because expanding is getting bigger. How fast is the volume changing? dv dt is what I'm hoping to find when each edge is 10. That's what I'm looking for. So what I'm going to do is I'm going to write down a formula for the volume of a cube. And that volume is going to be x cubed. So dv dt is 3x squared dx dt. Okay. They're saying find the value of dv dt when x is 10. So okay, that's going to be 3 times 10 squared is 100 times dx dt is also 3. So it's going to be 900. 900 cubic centimeters per second. Moving. The radius of a circle is increasing at a rate of 3 feet per hour. Find the rate of change of the area of the circle when the radius is 5 feet. Okay, so area of the circle is pi times radius squared. The given information is the radius is increasing at a rate of 3, so dr dt is 3. And let's see, find the rate of change of the area. So I'm going to take the derivative of area. And then I'm going to plug in, well, I've got dr dt. I've got r is 3, so that's 2 times pi times 3 times dr dt is also 3. Wait, no, that's not true. The radius was 5, right? It says right there, radius is 5 feet. So this wants to be a 5. All right, an object moves along the hyperbola xy equals 20 at a certain second, or in a certain instant, pardon me, x equals 4 and dy dt is 8. Find dx dt at that instant. Okay, well, I'm just going to start, they didn't give us y, right? We're going to need y, because this formula is going to have an x, a y, a dx dt, and a dy dt when I do the product rule. So I need to find out what y is in order to solve for dx dt. But if I've got x times y is equal to 20, I'm going to say 4y equals 20 at the time when x is 4, so that means that y has to be 5. So now I'm going to take the derivative of both sides of this equation with respect to time. So I'm going to use the product rule. So x times dy dt plus y times dx dt is equal to the derivative of 20 with respect to t, and that's 0. So now I think I've got everything I need. I've got x, y, dy, dt. I'm going to solve for dx dt, and so it should all be good to go. So x is 4, dy dt is 8, plus y is 5, dx dt is what I'm hoping to solve for, and that's equal to 0. So I'll be able to solve for dx dt by subtracting 32 from both sides and then dividing both sides by 5. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes, from 0 to 12. The graph of r is concave down. Okay, we don't really care that the graph of r is concave down. I know where this is going, and in a different part of this question, they would ask you to estimate the amount of air that got added in. And for now, we're just talking about related rates. We're talking about the rate at which air is escaping, or no, not escaping, it's getting added. But anyway, all right, so find the rate of change of volume of the balloon with respect to time when t equals 5. Okay, well, I know how to take the derivative of volume of a sphere. That's dv dt equals 4 pi r squared dr dt. And then, well, I'm going to have t equals 5. When t equals 5, the radius of the balloon is 30 feet. I was like, I'm missing some piece of information. So radius is 30 feet at the time we're interested in. And this is one of the only ones that I've ever seen you have to do anything that actually with the time variable. But notice that it doesn't matter. Now, dr dt is, so I'm just going to say that dr dt at t equals 5, well, that's what we mean when we write something like r prime of 5. Okay. So I'm going to pull in that r prime of 5 equals 2.0 right here. And then that's going to be the rate of change of volume. And indicate units of measure. We can do this, right? Because we know that the volume, if the radius is measured in feet, or the rate of change of radius is measured in feet per minute, but I'm pretty sure it's in feet. Well, the volume is in cubic feet. Per unit of time is minutes. So this is cubic feet, right? Yeah, feet per minute. Right, the top of a 25-foot ladder, these ladder problems are pretty much all the same, is sliding down a vertical wall, so maybe I'll just draw the wall right there, at a constant rate of 3 feet per minute. All right, so that means if I call this y and I call this x and I call this 25, because it's a 25-foot ladder, and as it continues to slide down, the length of the ladder will continue to be 25. I'm just going to say that, hold on, what am I going to say? Oh, sliding down the wall 3 feet per minute, that means dy dt is -3. Okay. When the top of the ladder is 7 feet from the ground, that would be y equals 7. What's the distance between the bottom, or the rate of change is the distance between the bottom of the ladder and the wall, right? We can probably figure out what the distance is just using the Pythagorean theorem. So x equals, all right, if you know your Pythagorean triples, you know 7, 24, 25 is going to be, it's a triple, so x is going to be 24. But if you're not sure about that, what you're going to have to do is you're going to say, hey, I know that x squared plus y squared equals 25 squared. Okay. And then y is 7, so 49 plus y squared equals 625. And then you'll find that y squared equals 500, and not 75, but 576. And then I guess you would take the square root of both sides and you would say y was either positive or negative 24. But probably positive because we're talking about a real scenario here, okay, with an actual length. All right. Now, I'm going to I need some derivative, right? I need to induce a dy dt to figure out dx dt. So I need a relationship, an equation that describes the relationship between x and y. And so I'm going to say that x squared plus y squared equals 25 squared again, because I've already got that. We know that's true. Okay, now if you don't know the triples and you don't know what 25 squared is, you're going to have to use a calculator for this, right? But I'm actually proposing that for this part, outside of the 24, if you didn't know what 25 squared was, you'd actually be fine to leave it like this, right? Because if I take the derivative with respect to time, I'm going to get something like 2x dx dt plus 2y dy dt equals the derivative of this number with respect to time, which has got to be 0 because it's just constant. And, well, it didn't matter that I didn't know what 25 squared was, right? That didn't actually play in at all. So if dy dt is -3, 2y is 48, 2x is 14 dx dt. That's what I'm hoping to solve for. Plus that is equal to 0. All right, 48 times 2 I'm good with, but 48 times -3, I don't know. I don't want to risk it, so I'm going to say dx dt is equal to positive 48 times 3 divided by 14. All right, and the last of the classic related rates word problems is the one about the Gazelle. Okay, one Gazelle is 4 miles east of an intersection. I've worked this problem before, so I'm going to say that's x equals 4, and it's moving toward the intersection at a rate of 19 miles per hour. At the same time, a second Gazelle is 3 miles to the south, so I'm going to call that -3 on y, of the intersection, traveling away from the intersection at a rate of 20 miles per hour. All right, so what I'm going to do, since I'm just going to act like this is x and y, and y is negative and decreasing. If you wanted to say this is y equals 3 and dy dt is positive, because you're thinking about just the triangle, not thinking about it on an xy grid, you'll get the same answer. But for me, I'm just looking at this, okay, I'm at the point 0, -3, or at the point 4, 0, and moving along the x-axis back that way. I think that's the easiest way to attack these problems. So we are talking about the distance between the two Gazelles. Okay. So I think I'm going to solve this one 2 ways. Since I'm, if you're only interested in the first way or the fastest way, then you can just skip forward in the video, I guess. But I'm going to say x equals 4, dx dt is -19, y equals -3, and dy dt equals -20. In that situation, I've got x squared plus y squared equals this distance, which I might call r squared. Okay. And so I can take the derivative of this with respect to time. I'll get 2x dx dt plus 2y dy dt equals 2r dr dt. Okay, so I've got most of the things I need ready to plug in, except for this r. But maybe I'll just wait for a second. 2x is going to be 8. Dx dt is negative 19. 2y is negative 6. dy dt is negative 20. All right, and that's equal to 2r, which I'm going to have to figure out what that is, times dr dt. But that's what I'm interested in solving eventually, right? I'm trying to find out what is dr dt. Is the distance between the gazelles increasing or decreasing? If I find that this rate of change of r is positive, I'd say the distance is increasing. If I find it was negative, I'd say the distance was decreasing. So at the time when x equals 4 and y equals 3, we have r equals the square root of 16 plus 9. Oh, it's 3/4. Oh, okay, I see that. For some reason, I thought it was 2 and 3. Okay, I thought we were going to have a bad radical. But that's really nice. Okay, so 2 times r is 2 times 5 is 10 dr dt. Okay, so I've got positive 120 minus, well, something that's close to 160, but definitely bigger than positive 120 and negative. So I'm going to say dr dt equals I don't even care. I just know it's going to be a negative number. So 8 times negative 19 plus 120, all divided by 10. And this is less than 0. So I'm going to say the distance is decreasing. I have lost the original front page, so I guess I'm going to have to go get one. So differentiate with respect to x, y is a function of x. Okay, we can do these. Just kind of bring out some scraps of paper for these. All right, so differentiate with respect to x. So this is the old implicit differentiation, right? So 4y to the first dy dx equals, wait, no, that's not equals, that's a minus. I can just, no, okay. Minus 12x to the third. We're taking with respect to x, so dx, that's just 1. That's equal to the derivative of 0 is 0. Okay, we're just taking the derivative of the equation, right? So that's good enough. Okay, over here for number 2, maybe I'll say okay, 2x negative 3x y squared. Okay, well, I'll take the derivative of negative 3x first, and that's negative 3y squared. I leave negative 3x the same, multiply by the derivative of y squared. Plus y to the 3, its derivative will be 3y to the 2 dy dx is equal to the derivative of 10, which is 0. Okay. Looks like, hey, we've got a couple more. Good, we got some transcendental here, that's good. That's what y'all need. Need that work. So we're going to start with the derivative of the outside. The derivative of the outside is going to be the derivative of cosine is negative sine. Leave the inside the same. Then multiply by the derivative of the inside. The derivative of a number times y would just be that number if we were taking with respect to y, but we're taking with respect to x. So I'm going to, hold on just a second. I'm going to multiply by pi dy dx. Minus 3 sine of pi x will be minus 3 cosine of pi x, leave the inside the same, and then multiply by the derivative of the inside. With respect to x, the derivative of pi x is just pi. And the derivative of 1 with respect to x is going to be 0. Okay, number 4, this is a product here. 4 sine x times cosine y is equal to 1. Okay, so I'm going to need to use the product rule on this left side. So I'm going to look at the first factor is 4 sine x, and the second factor is cosine y. So you know me, I want to do the easy one first. I'm going to take the derivative of 4 sine x, and that's going to be 4 cosine x. Leave cosine y the same. Then add in, leaving 4 sine x the same, taking the derivative of cosine y. Now the derivative of cosine of a thing is negative sine of that thing multiplied by the derivative of that thing. And so the derivative of cosine y is going, it's going to be negative sine y dy dx. And the derivative of 1 still 0. So that was just some good old-fashioned implicit differentiation practice, which I know a lot of y'all need right now, but you know, maybe you don't need that, and so if that's the case, you need to just focus on those related rate problems. Okay. Differentiate with respect to t. X and y are functions of t. All right, this could get annoying. So 4y to the first dy dt minus 12x to the 3, but now x depends on t, and that's equal to 0. I'll just go a little faster on these. Okay, number 6 is x squared. You can take that derivative, and that'll be 2 times x to the first times dx dt minus, 3. Okay, if I take the derivative of negative 3x with respect to t, I'll get negative 3 dx dt. Leave y to the 3 the same. I can already tell I'm going to run out of room here. That's all right. Just need another sheet of paper. So y to the 3rd. No, it's y to the 2. So I took the derivative of negative 3x and left y to the 2 the same. Now I'm going to leave negative 3x the same, and I'm going to multiply by the derivative of y to the 2. So that'll be 2 times y to the first, the rate of change of y with respect to t for the chain rule. Okay. Then this will be 3y squared dy dt, and that's going to be equal to 0 because still the derivative of that constant is 0. No matter which variable you're taking with respect to, the derivative of a constant is always 0. All right. Let's see. Maybe I can try. I'll be brave. Try to fit these in. So the derivative of cosine is negative sine. Leave the inside the same. Pi dy dt minus 3 cosine of pi x multiplied by the derivative of pi x with respect to t, and that's going to be pi dx dt. And that's equal to 0. Over here, 4 sine x cosine y equals 1. All right, so I got to do the product rule, and I know I'm going to need more room, so I'm going to go down here. I'm going to say the derivative of 4 sine x is 4 cosine x dx dt. Leave cosine y the same. Then I'm going to add, leaving 4 sine x the same. Taking the derivative of cosine y with respect to t will be negative sine y dy dt. And derivative of 1, it's 0. Those weren't the most exciting problems ever, but that was probably the type of practice you needed. And I like how I was drawing the distinction between taking the derivative with respect to x and with respect to t with things that have x's and y's in them. I think that'll actually be good for y'all to do. All right. Now we're talking about particle moving along a curve. Okay, this is something that we're going to talk about more in the second semester when we study parametric equations, but this is definitely, an equation that relates x and y, and x is a function of t, and y is also a function of t because the object is moving around, and you can envision x and y both changing as time passes. So we're going to just take the derivative of the equation. This is not one that we've taken yet, so the derivative of e to the x with respect to x. No, with respect to t. Okay, the derivative of e to the x with respect to t, well, it's like e to the x of t, right? The derivative of e to a thing is e to that thing But then we might have to multiply by the derivative of that thing. And the derivative of x with respect to t is dx dt. Okay. Now I'm going to have a product here, x multiplied by y to the third, so I have to use the product rule. And I'll start by taking the derivative of x with respect to t and leaving y to the 3 the same. And then add in, leave x the same, and take the derivative of y, y to the 3 with respect to t. Okay, that's my full equation. Oh, but hey, look at this. I've got x equals 0, but I don't have y equaling anything. So if x equals 0, I have 1 minus y equals 0. So that's going to be y equals 1. Okay, dx dt is 2. Find dy dt. All right, hold on. What am I doing here? Okay, so e to the 0 is 1. Dx dt is 2. Minus dy dt is what I'm hoping to eventually solve for. Equals dx dt is 2. Y to the 3 is 1. Plus x. So that's plus a 0 times some stuff that I don't really care about because I already have the 0 there. So I'm going to have 2e minus dy dt equals 2. So I'm going to say dy dt has to equal 0, right? If 2 minus dy dt equals 2. Okay. All right, y equals tangent x. This is one that the time for you to have this one memorized is coming very, very soon. Okay, I think you're going to need to know this one pretty soon. You need to be able to take the derivative of y with respect to t, but I know y'all can do that. Y'all were able to do that in class for me. And tangent x, I hope for the best, but squared, leave the inside the same, and multiply by the derivative of the inside. The derivative of the inside is the derivative of x with respect to t, and we call that dx dt. Right? X equals pi over 3, y equals the tangent of pi over 3. And I'm liking this problem set because it's got the transcendental functions, it's got some unit circle on there. I think it's really healthy. So negative pi over 3 is going to be down here because I know the pi's over 3 sit at a 60-degree reference angle. So I'm going to go down here. I'm going to draw the triangle. The hypotenuse is always 1. Okay, the short leg of a 30, 60, 90 is a half, and the longer leg is root 3 divided by 2. Except that since we're in the fourth quadrant, I know that's where y is going to be negative, so I'm going to call that negative root 3 divided by 2. All right, and okay, so dy dt is secant squared x dx dt. So, if that's x, my angle secant is the opposite of cosine. Secant is going to be 1 divided by a half is 2. So dy dt equals 1 over a half squared, so that's 2 squared is 4, times dx dt is 2, and that's going to be 8. Okay, I think these are going to be pretty similar to the ones that I just did. Yeah. All right, so when x is equal to 4, y is equal to the square root of 4, which is 2. Okay. And then, well, I've got y equals square root x, and they're functions of t, so I need to take their derivatives with respect to t. So dy dt equals, this is x to the 1/2 power, or x of t to the 1/2 power, so it'll be 1/2 x of t to the negative 1/2 power, times the derivative of x with respect to t, which, sometimes you might call x prime of t, but with related rates, we really like to use dx dt. So I'm going to, here, I think I'm ready to plug stuff in, right? I've got dx dt, I've got x equals 4, I've got y equals 2. Evidently, I don't actually need y equals 2. So, okay, dy dt is what I'm hoping to find, 1/2 of 4 to the negative 1/2 times dx dt, which is 3. Okay. Free response, happy to stay there, but I know that a lot of people in my class got hit by this on multiple choice, 4 to the negative 1/2 power. There was a problem that required you to evaluate that number. And, well, they didn't have this as an answer choice in the multiple choice scenario, and a lot of people were kind of left out in the cold. So I just want to remind you that the 1/2 power is the square root, and the negative 1 power is, making it 1 over 4. So this is 1/2 times 1 over the square root of 4, because that's what the negative 1/2 power is. It's 1 over the square root of x, multiplied by 3, so I've got 3, and that looks like 3/4. That one in there. XY equals 4. I mean, we did a very similar problem to this on the XY equals 20, but, never bad to keep practicing. If x equals 1, y is pretty clearly going to be equal to 4, not 1. And so I can take the derivative of this with respect to time. X dy dt plus y dx dt equals the derivative of 4. Okay, find dx dt when x is equal to 1 and y is 4. So given dy dt is negative 6. So x is 1, dy dt is negative 6, plus y is 4. Trying to find dx dt, and that's 0. Okay. So negative 6 plus 4 dx dt equals 0. I'd say that 4 dx dt equals positive 6, but then I'm going to divide by 4. I get 6/4. I'm happy. You can call that 3/2 if you want. That'll be all for this video. I'm definitely going to record another video of more examples of related rate questions, because this is something that, some people have traditionally found pretty challenging, and they just need more practice, than this set of problems is providing. And I get that. So I will provide that for you. You'll see it on the calendar where you normally find extra practice worksheets, and that'll just be a separate video on my channel called probably more related rates examples or something like that. So thanks for watching.